Yes, sir.
Okay. So today we are going to talk about linear discriminant functions. This is one of the important topics in machine learning and pattern classification. So we need to introduce this linear discriminant function to understand many other classification techniques. So before we talk about linear discriminant function, so I just want to recall what we have learned from density estimation and Bayesian classifier. So if we see both these techniques like maximum likelihood and Bayesian parameter estimation techniques, then what we have assumed there that the forms for the underlying probability density functions are known. That means whatever the density that we estimate, so for that the underlying probability density functions are known. Now we can use the training samples to estimate the values of these parameters. Okay, so if we want to estimate the values of certain number of parameters, then we can use the training samples in both maximum likelihood and Bayesian parameter estimation. Now, when we introduce the linear discriminant function, so here we have to assume that the proper forms of the discriminant functions are known. Okay, so here we claim that the proper forms for the discriminant functions are known and use the samples to estimate the values of the parameters of the classifier. Okay, so here we assume that the discriminant functions are known and we can estimate the values of the parameters from the given samples. Now, among the discriminant functions, some discriminant functions are statistical and some of them are not statistical. So, when we will be talking about support vector machines, so we need to understand the underlying concept of discriminant functions, and then only we can initiate the discussion about support vector machines and other statistical or non-statistical discriminant functions. Now, linear discriminant functions have a variety of analytical properties. Now, they can be optimal if the underlying distributions are found to be cooperative. Okay, so they can be found or they found to be optimal if the underlying distributions are found to be cooperative, such as what we have learned from Gaussians, that the Gaussians are having equal covariance matrices. Okay, so when we have a number of Gaussian functions, so for each function or for all the Gaussian functions, we can have the equal covariance. So that we have seen in case of Gaussian mixture models or other Gaussian functions that we have considered. So your linear discriminant functions are relatively easy to compute, and linear classifiers are attractive candidates for initial and trial classifiers. Okay, so these are the some of the analytical properties of linear discriminant functions. Now, when we formulate the linear discriminant function, so linear discriminant function is formulated as a problem of minimizing a criterion function. That means when we will be working on a particular linear discriminant function, so we have to find out the criterion function, and based on the criterion function, we can assign the class level to the query samples or query feature vectors. So here the here the objective of getting linear discriminant function is the and then so this linear discriminant function is posed as the problem of minimizing the criterion function. The criterion function that we obtain is to be minimized. Okay. Here the criterion function for classification is the sample risk. So what are the criterion functions that we can obtain for the classifications? So one of the criterion function is sample risk, or if we consider the other criterion function like training error. So this training error is obtained on the set of training samples. That means when we perform the training of the model or the classifier with training samples, then we can estimate the training error, and this training error becomes the criterion function for classification. Now it is difficult to derive the minimum risk linear discriminant, and for this reason it will be suitable to investigate several criterion functions that are analytically more tractable. Now if we want to have the relevant criterion functions, then we can get the relevant criterion functions, so which are found to be equivalent to the initial consideration for the criterion functions. So we can have the sample risks or training error, but if we have other criterion functions, so we can get the other criterion functions, and which will be found to be equivalent to the initial consideration. Now our attention will be devoted to studying the convergence properties and the computational complexities of various gradient descent procedures for minimizing criterion functions. Now, if we look at logistic regression or linear regression, so what we have found that after having the decision boundary, so we can define the error function. Okay, and from there we can try to minimize the error function. So it has the error function is nothing but the criterion function, so which is defined over the decision boundary. So similarly here we can get the same criterion function, and over which we can get the we can get the minimization of the criterion function, and for that we need to study the convergence properties and the computational complexities of various gradient descent procedures. So here we can introduce the various gradient descent procedure to obtain an optimal value for the criterion function. Now what is decision surface in linear discriminant function? So let us consider there is a linear discriminant function, so which is the linear combination of different features. Okay, now if we consider the linear discriminant function is gx, then this gx is given by wtx plus w0. Now here w is the weight vector and w0 is the bias or threshold weight, and here x is the feature vector. Okay, so this gx is the discriminant function, which is given by w transpose x plus w0. Here w is the weight vector, okay, and w0 is the bias or threshold weight, and here x is the feature vector. Now this linear discriminant functions which are studied for two categories. So here we can study the linear discriminant function for two category, multi-category and general case. So what you know about two category, that there will be two different classes, and multi-category there will be more than two classes. But if we consider the general case, then this general case there will be a C such discriminant functions. Now if C is the number of discriminant functions, then one discriminant function will be used for each of the C categories. Okay, so if we have C number of classes, okay, and there will be a C number of discriminant functions, then here each discriminant function will be used for each category. Okay, so here we have shown the division of discriminant functions. So there are three different types of discriminant function that we can define for two category classes, for multi-category classes, and for general cases. Okay. Now we will consider the decision surface for two category. Now for a discriminant function, the two category classifier will implement the following decision rule. Okay. Now what is the decision rule? So we will decide W1 if g of x greater than 0. Okay. Now, if we see this function gx equals to w transpose x plus w0, so here wtx, this between w transpose and x, so we can see that there is a dot product. That means this is the linear combination of weight values and feature values, plus we get the threshold weight or bias as w0. Now, if this gx is found to be greater than 0, then what we decide, that we decide w1. That means if gx is found to be greater than 0, then we will decide w1. If gx is found to be less than 0, then we will decide w2. That means here w1 and w2 are two different classes. Since we are considering two category case, so here we have to consider two different classes. So for two different classes, we can consider w1 and w2. Okay. So we can consider W1 as the positive class and W2 is the negative class. So whenever we will see that Gx is found to be 0, then we will assign the feature vector x to W1 or positive class. Or when Gx is found to be less than 0, we will assign x to W2. That means in the negative class. So here x is assigned to W1 if the inner product means the W transpose x will exceed the threshold. Okay, exceed the threshold minus W0. So how can I get the minus W0? So if we make gx equals to 0, then what we get, W transpose x plus W0 equals to 0. Okay, and if we take W0 on the right hand side, then we will get W transpose x equals to minus W0. Now, if we get this dot product greater than 0, okay, that means if this dot product W transpose x exceeds the threshold minus W, then we will assign the feature vector x to W1. Otherwise, we will assign the feature vector x to W2 class. Okay. So this is for this is for the positive or negative classes. So when we have two different classes W1 W2, then according to the criterion functions, we can get the feature vector uh, in uh, in one class among two given class levels. Okay. Now you can imagine another situation where we get gx equals to 0. Okay. So when gx equals to 0, here x can be ordinarily be assigned to either class. That means whenever gx is found to be 0, that means we can say that x is lying on the decision boundary or decision surface. So in this situation, we can assign, either we can assign x to w1 or we can assign x to w2. Since here x is found on the decision surface, because whenever the x will be found on the decision surface, we can get dx equals to 0. Okay, that means the class is found to be undefined, the class level is found to be undefined. So in this situation, we can, what we do, we get this x either in w1 or w2. Now this what does this mean when we write gx equals to 0? So this equation gx equals to 0 defines the decision surface. Okay, and this decision surface separates the points assigned to w1 from points assigned to w2. That means if we, since we are considering two category case, that means there are two different classes w1 and w2, and this decision surface separates these two regions. Okay, so one region comes under w1, another region comes under w2, and this decision surface gx equals to 0 defines this separation between these two regions. Now, if gx is linear, okay, uh, then this decision surface is a hyperplane. So what we know from our previous discussions, that whenever we have a single feature or single dimensional feature or one dimensional feature, so we get the decision surface or decision boundary as a point. Okay, and whenever we have two dimensional features, then for two dimensional features we get the decision boundary as straight line, and when you get more than two dimensional features, so we get hyperplane. Okay, or we can say for three-dimensional features we get a plane, and more than three-dimensional features we get hyperplane. Now in this case, for two category case, we say this decision surface is a hyperplane. So here gx is denoted as hyperplane. Now if x1 and x2 both are decision surface, now let us imagine a situation where x1 and x2, if we consider x1 and x2 are feature vectors. Okay, now these two feature vectors are found on the decision surface. So whenever these two feature vectors x1 and x2 will be found on the decision surface, so for x1 we can write gx1 equals to 0, and for x2 we can write gx2 equals to 0. Okay, now we are equating these two functions. So when we will be equating these two functions, what we can get? We can get W transpose x1 plus W0 equals to W transpose x2 plus W0. Okay, or we can write, so we get the common from both these. Uh, we can get the common of this weight vector W transpose from both these terms. Okay, and we get W transpose into x1 minus x2 equals to 0. On both the sides, W0 gets cancelled. Okay, that means the bias gets cancelled, and we take W transpose x2 on the left hand side, and we take the common W transpose, and it will be multiplied with x1 minus x2, and we can write this equals to 0. Now what interpretation we can make from this? So from this equation, so we can make the interpretation that here W is normal to any vector. Any vector means either x1 or x2. So we can get the W is normal to any vector lying in the hyperplane. So as we have considered the hyperplane is gx equals to 0, so therefore when x1 and x2 will be found on the hyperplane, so therefore w this weight vector will be found to be normal to any vector which is found on the hyperplane. So here in general, we can say that the hyperplane H divides the feature space into two half spaces, decision region R1 for W1, that means for positive class, and region R2 for negative class W2. Okay. Now, if we consider the hyperplane is denoted by H, then this H will divide the entire feature space into two different half spaces. Okay, so one decision region R1 for W1, that is the positive class, and region R2 for W2, that is negative class. Now because gx greater than 0, if x is in R1, so it follows that the normal vector W points into R1. Okay, and it is sometimes said that any x in R1 is on the positive side of H, and any x in R2 is on the negative side of H. Okay, so as I said in the earlier, whenever we get these functions found to be 0, then x will be found on the positive side, otherwise it will be found on the negative side. Now if we look at the geometric interpretation about decision surface for two category, then here we can see that here we actually consider the decision boundary or decision surface. So this decision surface separates the feature space into two half spaces. Okay, so one half space is for positive class, that is R1. Okay, so this feature space represent this half feature space represented by R1, and another half feature space is represented by R2, and in between them here we get the hyperplane. Okay, so equation of this hyperplanes becomes gx equals to 0, and this is the weight vector. So this weight vector is making, this weight vector is found normal to the hyperplane. Okay, now if any feature vector among x1 and x2 is found lying on this hyperplane, then this weight vector will be found normal to that feature vector x1 or x2 which is found on the hyperplane. Okay, the discriminant function gx will give an algebraic measure of the distance from x to the hyperplane. Okay, so here gx gives an algebraic measure of the distance x from the hyperplane. So what is x? So if we consider this is a feature point or a feature vector x, so from this uh, so from this point we get a distance to the hyperplane. Okay, so now if we get, if we want to express the x or the feature vector, then we can write x equals to xp plus r into w by norm of w. Okay, so this is w by what is w by norm w. So here we get a distance from the origin to the hyperplane, and this is denoted by w0. Okay, or this is denoted by w, and we get the normalized form of this w by dividing it dividing this w by norm w. Okay, now what is r? Now what is r? R is the distance to the hyperplane from the feature point x. Okay, and xp is the point on the hyperplane. Okay, so that means this xp is found as the normal projection of x. So if we get the projection of the feature vector x onto the decision surface or the hyperplane H, then we get that normal projection as xp. Okay, so what we are doing here, we are getting the normal projection of x, that is xp, plus r is the distance between the feature vector x and the hyperplane H, and here we are normalizing the w, that is the weight vector, which is found to be normal to the hyperplane. Okay. Now, since g of xp equals to is found to be 0 because xp is lying on the hyperplane, that is why we can write g of xp equals to 0. Now, what we are doing, first we get this formulation for the normal projection of x, okay, onto the hyperplane H, and then we rearrange these terms. We rearrange these three terms, and we are writing xp equals to x minus r into w by norm of w. Okay, so for if we get this xp, if we get this xp in this equation, so what we get, we get g of xp equals to wt into x minus r into w by norm of w plus w0. Okay, equals to 0. So what we are getting, we are getting the value of xp, that means we are getting the normal projection of feature vector x into this equation. Okay, into this equation, So here we are putting the value of normal projection, that is the normal projection of x, into this equation w transpose xp plus w0. Okay, so if we rearrange these terms, so we are getting g of xp equals to w transpose into x minus r into w by norm of w plus w0 equals to 0. Okay, so from here we can write here we get that w transpose x, okay, w transpose x minus r into w transpose, making dot product with w divided by norm of w plus w0 equals to 0. Now for w transpose w we can write the square of this norm, okay. W transpose w we are getting the square of this w, okay. And when we write this when you write this square of w over this in this equation, then what we get, w transpose x plus w0, that is this is the bias, minus we can write gamma of gamma of w equals to 0. Now here w transpose x plus w0, so we are taking this we are taking the third term on the right hand side, and we can write w transpose x plus w0 equals to gamma into w, okay. And so here r is given, here r is given by gx divided by w, okay, gx divided by w. So so this is nothing but we are rearranging these terms, and we try to estimate the decision boundary for the normal projection for the given feature vector x, okay. Now the distance from the origin to the hyperplane is given by w0, this is w0 divided by norm of w, okay. So this is the distance from the origin to the hyperplane, and which is given by w0 by norm of w. Now whenever w0 is found to be 0, the origin is on the positive side of w, okay. So as we can see from this geometric interpretation of decision surface, that whenever we will get w0 is found to be greater than 0, then the origin will be on the positive side of hyperplane, or if we get w0 less than 0, then it will be on the negative side. So from this established convention, we can get this we can get the position of the origin about or with respect to the hyperplane. Now if we get w0 equals to 0, then the decision surface will have the homogeneous form w transpose x, okay. And the hyperplane will pass through the origin, so whenever we get w0 equals to 0, that means whenever the bias is found to be 0, then the hyperplane will pass through the origin. So here the linear discriminant functions divides the feature space by hyperplane decision surface, and the orientation of the surface is determined by the normal vector w. So here the normal vector w decides about the orientation of the decision surface, okay. So if the normal vector is getting changed, then the orientation of the decision surface will also be changed, okay. And if we look at the location of the decision surface of the hyperplane, so this decision surface location of the decision surface is determined by the bias w0. So what we have obtained about so what we have seen about the bias or the threshold value w0 is that whenever w0 is found to be 0, then on the origin will be on the positive side. Whenever we will get w0 less than 0, then the origin will be on the negative side, and whenever w0 is found to be 0, then the hyperplane will pass through the origin, okay. So that means the location, we can decide the location of the decision surface on the hyperplane by looking at the value of the bias, okay, or threshold weight. And So from here we can get to important information. So one information about the orientation of the hyperplane of the decision surface, and another important information is the location. So location of the surface. So here the orientation of the surface is decided by the normal vector W, and the location of the decision surface or the hyperplane is decided by the bias value W0. Okay. So here the discriminant function gx is found to be proportional to the sine distance from x to the hyperplane. Now here with gx greater than 0, so we can say gx greater than 0 when x is on the positive side, and gx less than 0 when x is on the negative side. Okay. If you have any questions, you can ask me. Otherwise, we will stop now. So today we are not discussing a new topic, because when we will start a new topic in the next class, so we need more time. So that is why we stop now. And tomorrow there will be no class. Okay, tomorrow I will be on duty leave. So tomorrow there will be no class. So next class will be held on Thursday. Okay, that's all for today.